video, you're going to learn how to calculate empirical formulas from data that you're given. Now, the empirical formula by definition is the smallest whole number ratio of elements in a compound. There are some steps that you're going to use in calculating this formula. And the first step is you look at the data that you're given, and if you're given percents, like percent composition, we did that prior to this video. We did it on Friday. So if you're given percents, then you have to assume you've got a 100 gram sample, and then you just change that percent to a gram. If you're given mass, then you can skip straight to step number 2 and change each of those elements' mass into moles. After you do that, you're going to divide all the molar quantities by the one that is present in the smallest amount. And if you end up with whole numbers, when you do that, you're finished. You just write the formula. If you don't end up with whole numbers, then you're going to do this step in number 5, which says you're going to multiply all the quantities by a factor that will put them all into whole numbers. Once you have all whole numbers, you're going to write the formula. Now, I know these steps may not make any sense to you right now until you see an example. So I have 2 examples that I'm going to do in this video. Now, I would suggest that if you want to write these steps down, you can pause the tape, copy them down, and then proceed on to the next slide with me. All right, example problem 1. This is very similar to what you would see on a quiz or a test or something like that. Now it says you have this unknown substance, and laboratory analysis has determined that it contains 36.5% sodium, 38.1% oxygen, and 25.4% sulfur. So if we assume that all of this is based on a 100 gram sample, then that automatically changes these percents into grams. So that's what we're going to do. We're going to assume that we have a 100 gram sample, and that instead of 36.5% sodium, we have 36.5 grams of sodium, and likewise with the oxygen and the sulfur. So according to step 2, the first thing I'm going to do, once I know how many grams I have, is to change it to moles. So I'm going to just do my DA table, write down what I've got, 36.5 grams of sodium. And I'm going to change that to moles. So if you remember from a prior class, you change it to moles by multiplying by the molar mass, so that your grams cancel and you're left with moles. So if I look on my periodic table for sodium, it's on the next slide, you can see that sodium has a molar mass of 22.99. So that's what goes on the bottom. Grams in 1 mole. Now it looks like I didn't need that line to be quite so large. Alright, so I'm going to plug that in on my calculator. 36.5 grams divided by 22.9, and I get 1.59, and that's moles of sodium. I'm going to do the same thing for oxygen. 38.1 grams of oxygen based on our 100 gram sample. And in 1 mole of oxygen, I have 16 grams of oxygen. I just know that by heart. If you want to look on the periodic table, you're more than welcome to do so. And when I type in my calculator 38.1 divided by 16, I get 2.38. Now, if I'm going too fast for you, you're more than welcome to pause the video and plug it in on your calculator and generate the answer. Sulfur is 25.4 grams in this sample, and the molar mass of sulfur is see, 32.065, so I'm going to round that to 32.07. grams of sulfur. All right, now I plug that into my calculator, 25.4 divided by 32.07, and I get 0.792 moles of sulfur. Now, once you've changed all of this to moles, your next step is going to divide each one of these molar quantities by the one that is present in the smallest amount. Now, if you look here, the one that is present in the smallest amount is sulfur. So that's what I'm going to do. I'm going to divide each one of these by the moles of sulfur that I have found in this compound. And that's 0.792. Okay, now you can pause the video. I'm going to pause and I'm going to do my calculations. So you do the same. All right, after doing my calculations, I find that the ratio of sulfur to sodium is a 2-to-1 ratio. So that means for every 1 mole of, or for every 1 mole of sulfur, I'm going to have 2 moles of sodium. So that's a whole number. Likewise with oxygen, for every 1 mole of sulfur, I'm going to have 3 moles of oxygen. And so because all of these are in whole numbers, I can write my chemical formula and not have to worry about the last step. So here I'm going to have Na2, see how I've calculated there's 2 moles, so that's how many moles I have in the compound. O3 S. Now, you might look at that and think, oh, that kind of looks familiar. S and an O3, or an O3 and an S. If you were to look on your polyatomic ion sheet, you would see that this right here, when you have 1 sulfur and 3 oxygens, that is a polyatomic ion called sulfite. So you can rewrite this to reflect that you know that that's a polyatomic ion called sulfite. And so I can rewrite this. I'm going to just do it over here on this side since I have more room. Na2SO3. And that's my answer. This is sodium sulfite. Okay, that wasn't very hard. So let's go on to another example. All right, we're going to do this problem here. Start out with some orange. All right, now according to the first step, if you're given a percent, you assume that it's a 100-gram sample and you change that mass to moles. So according to this, I have 38.4 grams of potassium, and I'm going to change that to moles of potassium. 1 mole of potassium is equivalent to 39.1 grams of potassium, so you may want to look on your periodic table and confirm that. When I do that calculation, I get 0.982 moles of potassium. Now I'm going to do oxygen, 36.3 grams of oxygen. In 1 mole of oxygen, there are 16 grams of oxygen. When I do that calculation, I get 2.27 moles of oxygen. And then I have to do carbon, which is 23.7 grams. the molar mass of carbon is 12.01 grams per mole. When I do that calculation, I get 1.97 moles of carbon. And then the last one I'm going to do is hydrogen. 1.66 grams of hydrogen. Ooh, that's a crooked line. And in 1 mole of hydrogen, I have 1.01 grams of hydrogen. And that calculation gives me 1.64 moles of hydrogen. Now, if you need to stop the tape or pause it right now so that you can confirm all this math, please do so, and then you can come back. So now I look at this and I decide which one of these quantities is the one in the smallest amount. And of course, you see that it is potassium. So I'm going to divide each one by that molar quantity of potassium. And when I do, it's going to give me that relative ratio of these elements based on the smallest amount, or the one in the smallest amount. So I'm going to pause to do my calculations. You do yours. All right, I hope you found these same answers that I did. And if you look, this one is a whole number, this one is not. So you need to recognize the fact that 2.31, that 0.31 is almost a third. So you need to recognize that. And that this right here, this number is not exactly 2.00, but it's close enough that we can round it. So we can round that to 2 and say that's exactly 2 moles. This one right here, though, you can't round that. It's not close enough to round. And you should recognize that 0.67 is approximately the fraction 2/3. So I need to pick a number to multiply all of these molar quantities by to ensure that I have whole numbers. I'm going to change my color for just a second. See if this one will work. So as you can see, this is 2 1/3, and this one down here is 1 2/3. So I'm going to multiply all of these quantities by 3. Because when I multiply by 3, it's going to get rid of this fraction, this decimal. And you can confirm this just on your calculator that we're going to get approximately, or we're going to get very close to whole numbers here. So that's going to be about, well, it's exactly 3. So that'll be 3 moles of potassium. And right here, 2.31 times 3 is going to give you 6.93, which is very close to a whole number. And I can round that one. See, I don't think, oh, it's not going to let me write there. That's okay. That's moles of oxygen. And then right here, you know, that's going to be about 6, exactly 6. 2.01 times 3 is 6.03. So that's close enough to round. 6.03 moles of carbon. And then right here, 1.67 times 3 is going to be 5.01 moles of hydrogen. So now that I have these whole numbers, or I have this one right here that's, and this one, these 2 or 3 that are very close to whole numbers, I can round them. I can go ahead and write my formula.